Well, good afternoon, everybody. I know we've, been here for a while, so I won't take too much of your time. I know we have a social hour after this, and see some of you guys eyeballing those door prizes just like I was. But I'm here to talk about modeling surface mine use for potential bioenergy crop development. I'm listed here, but as well as my school advisors as well. All right. So I am funded by the Mass Bio Consortium, which is the Mid-Atlantic Biomass Consortium. It is a USDA NEFA-funded project, $10 million over the span of 5 years. We are currently ending our third year, so we still have 2 years left. And we partner with schools such as Virginia Tech, Penn State, and University of Georgia, and they're all listed at the bottom as well. Some of the Mass Bio goals are to deliver sustainable and economically feasible biomass for value-added products system in the Mid-Atlantic region. Mid-Atlantic region being, I don't have a map of it, well I do eventually, but it's New York all the way down to Kentucky. And the next one that I'll be highlighting is to promote the regional bioeconomy. Some of our collaborators and study sites, so as I said in this map, we go from New York all the way down to Virginia. We leverage and use available resources from the region. So within this region, we have over 10 million acres of mined and marginal lands. 1,200 of those acres currently have hybrid willow and switchgrass on them with 30 or more established sites. And our goal is to develop at least 20 more new sites within the 5-year project. A little background on surface mining. In West Virginia, it began in the early 1900s. Before the SMACRA enactment, little to no mines received any type of reclamation due to the lack of legal requirements for it. And so a lot of those mines have either reclaimed naturally or are still in the unreclaimed state. It was enacted in 1977. After that, it did require some sort of reclamation effort, and a lot of the times the coal mining operators and companies chose for the less expensive, less time-consuming reclamation effort, which was just planting grass, revegetating as much as they could. Currently, surface mining in the Appalachian region has served large forested areas, and more than 600,000 hectares have been mined since 1977. Like I said, the reclamation efforts pre-SMACRA were not that great. Post-SMACRA, they are just revegetating as much as possible. But it has been proven from previous studies that biomass production on reclaimed surface mines can be successful under certain criteria. Biomass production also can directly sequester carbon, which, with everybody's goal of meeting those net zero goals by 2050, this is the best way to do it. Carbon sequestration rates with grass range from 0 to 1 megagrams per hectare per year. In forest ecosystems, it's 0.7 to 4. In another study, it showed that proper land restoration on surface mines could offset 16 teragrams of CO2 annually in the U.S. Bioenergy feedstocks. So some of the environmental benefits of this is it reduces soil erosion, so protecting it from major water events. It mitigates climate, like I just mentioned, and it also allows us to maintain the health of the environment and watch that restoration process to make sure that it's happening properly. Biomass crops are also used in producing biofuel production and other sources of energy, so they're not just to sequester carbon. Now, you're asking, why is this important? A significant number of companies have actually made the net zero pledges by 2030 and 2050. We have reports as large as 400 of these companies, and 38% of them being Fortune 500, have set these milestones for 2030, which it's 2023, where you have 7 more years to do this. And a lot of the times, generation of carbon offsets is very important to meet these companies' ESG goals. Not sure if anybody knows, but the SEC is still working on whether requiring publicly traded companies to report their carbon offsets and their ESG reports. So, to get into the nitty-gritty of my study, the objectives were to quantify vegetation growth over an 8-year period, looking at grass, shrub, and forested areas, identifying suitable acreage for biomass and or energy crop development, and lastly, identifying to survey these landowners for their willingness to engage in the bioeconomy. So, the first thing I did was look at past, current, and change in the land cover status on surface mines. To do this, I used the West Virginia Department of Environmental Protection's surface mine permit boundary data, a really big set, shrunk it down to only surface mines. I also looked at the Multi-Resolution Land Consortium's National Land Cover Database, 2013 land cover, and 2021 land cover. And I determined the acreage in grass, shrub, and forest using their legend, and then I determined the acreage change from 2013 to 2021 in grass, shrub, and forest, all using the change detection wizard in ArcGIS Pro 3.0. The next method was the suitable acreage. So using only the newest data, 2021, from the NLCD, I looked at grass and shrub. I also used a DEM of 5-meter resolution, which I converted to slope and percent rise. And then I isolated the 15% or less slopes due to previous literature stating that agricultural equipment to harvest these bioenergy crops can operate on 15% or less slope. And I used that using the fuzzy membership function. And then I determined the acreage that met the slope and the land cover by multiplying them. Method 3, so development efficiency. So this has to be economically feasible. You can't just plant or reclaim half an acre and then expect it to have these big benefits. So in order to do this, I took the raster data and I converted it to polygons, and then I sorted it in 10-acre increments all the way up to 50 acres. And then from there I found their acreage size, and then I again repeated this for the shrub. And then lastly, I looked at ownership. So I used the West Virginia tax parcel data that was updated as of July 2023. And in the future, which I'll talk about later, I plan to survey the owners on their potential to use biomass plantings or to engage in these nature-based programs. The results. So, I found that in 2021, there were over 68,000 acres of grass on these surface mines, and 37,000 of shrub, and over 200,000 of forest. Looking at the land cover change status, a lot of the land actually didn't change, but from grass to shrub, over 12,000 acres was changed, and then from shrub to forest, over 11,000. And we looked at this because as we progress from grass to shrub and shrub to forest, you're sequestering more carbon as the plants get bigger. So a lot of times that these lands are not a part of these carbon programs, they're not receiving these credits, they're not being used to their maximum value. So then I looked at suitable acreage. These numbers are a little bit inflated due to the 30-meter land cover resolution that I used compared to the 5-meter elevation that I used. So in efforts to be more accurate, I will go back and redo that with a newer land cover set. But because we use the 15% slope, these numbers are a lot higher. In previous studies done in 2012 by my professor, they used 10%, and then I had a colleague at Penn State use 8.75, so there are differing slopes. And as your threshold declines, you have less and less acreage. Now looking at the economic feasibility, just only at 2021. Obviously, as we have 10-acre sizes or more, we're going to have more suitable acreage contiguously. And then as we go down, as we go over to 50, we go down in our available acreage. But it was pretty consistent across the board in terms of grass compared compared to shrub. And then I looked at ownership, which was the last thing, and I found that over 1,700 tax parcels were identified to have these greater than 10-acre contiguous areas on it, 68% being grass, 32% being shrub. I then separated the owners into private business owners, private individuals, and then public, with approximately 225 being private business, over 300 being private individuals, and then 17 being public. And in total, 540 landowners were identified. So then the potential crop development of switchgrass on these areas that we identified as grass and suitable, using the 10 acres, the yield per year came out to be just under 400,000 metric tons of switchgrass that can be produced on the surface mines that I identified. And then as we go to the 50 acres, it does decrease, but that's still a significant amount. For future work, I will survey these landowners, and I'm hoping to have a high response return, whether it be positive or negative. And then the next thing to do is look at the carbon value. So what is the natural carbon storage of these mine lands are going from grass to shrub to forest? So I did mention that earlier. So the next thing I'll be looking at are the carbon sequestration rates that are occurring on those mine lands. That just does take a little bit more time to research. And then the ecosystem value. What in terms of ecosystem values are not being maximized? So really, how can these lands, like I mentioned earlier, that are just sitting there, possibly not being utilized to their potential, whether it be private business owners or private individuals, and even the public. Like I mentioned earlier, I did have some limitations. I did use a 30-meter resolution land cover data set due to the fact that it was 2021 data, so it was the newest land cover data I had public access to. But one of my other professors recently came out with the 2020 West Virginia land cover data using NAPE imagery, so I will be going back and using that, and using 2011, 2016, and 2020 to again evaluate the change over time. I will be resampling slope from 5 meter to 30 meter to reduce that emphasis in the suitable acreage that I found in my methods section. And then the conversion from polygons to the polygons when looking at contiguous acreage did have some effect on it as well, since not everybody's land is going to be a 30 meter by 30 meter square. But that is all I have. So I will take questions. Thank you.